Well, hello friends, here we are again, and we're going to talk more about using Laplace transforms. Yesterday or day before in lecture we introduced the topic. Today I want to work another problem using what we learned a couple days ago and solve this equation, x double prime plus x equals cosine 3t, where x of 0 is equal to 1 and x prime 0 is equal to 0. So it's an initial value problem. The independent variable this time is t. The dependent variable is x. It's second order. It does have constant coefficients, and it is a non-homogeneous with a cosine function for the f of t, which appears on the right. So let's see what we could do. We could solve this using methods that we knew a week and a half ago, but we can also see if we can't solve this with Laplace transforms. So one of the first things we learned was that the Laplace is a linear operator. And so I'm going to write L double prime t plus the Laplace of x. I think I said L double prime t pretty clearly. That's L double prime x plus the Laplace of x is equal to the Laplace of cosine 3t. Left side, right side. Now we have a division theorem that tells us about expressing the Laplace of x double prime. And so using that theorem, this would be s Laplace of x minus s x of 0 minus x prime of 0. So that's using the derivative theorem on the L of x double prime. Now I've got a plus L of x. We'll just leave that one alone because actually what we want to do is to find out what L of x is. And so we'll just leave that one where it is. Now what in the world is the Laplace of cosine 3t? Well, we've got two options here. We know what the definition of the Laplace is, and so we could write down the definition of the Laplace of 3t and integrate and see if we couldn't come up with an expression for the Laplace of cosine 3t. That was one option. And the second option, and the more practical one, is that we look in the inside cover of our book or anywhere else where we've got a table of Laplace transforms, and we look up the Laplace transform of cosine 3t. And if we do that, we'll find, this is just inside cover of our textbook, it's going to be s over s squared plus 3 squared, and I'll write 3 squared as 9. Okay, now we're doing algebra, and that's the whole point of Laplace transforms. It's to take a differential equation problem and turn it into an algebra problem, because algebra problems are usually easier to solve than differential equation problems. So let's get the L of x's together over here, and I would have a coefficient s and a coefficient of 1. So I would have, you know what, I wrote this wrong also. That's an s squared. I'm sure glad I caught that right now. Check the theorem for the Laplace of x double prime. I just wrote it wrong. So I would have an s squared plus 1 Laplace of x, and then the initial conditions tell me x of 0 is 1, tells me that's 1, so I'd have a minus s, and x prime of 0 is 0, so that doesn't contribute anything. And there's the left-hand side. And the right-hand side is s over s squared plus 9. Let's transpose the s, and so I get an s squared plus 1. Laplace of x is equal to s over s squared plus 9 plus s. And now divide by s squared plus 1, and I get Laplace of x is equal to s over s squared plus 1 s squared plus 9 plus s over s squared plus 1. Now I'd like to have a common denominator here, and so to get the common denominator, if I would multiply numerator and denominator by s squared plus 9, s squared plus 9, then you see that I've got a common denominator, and this would be equal to, expressing them over the common denominator, would be s plus, this would be s cubed plus 9s over s squared plus 1 s squared plus 9. And in fact, here's an s and here's an s. This would be s cubed plus 10s over s squared plus 1 s squared plus 9. So the Laplace of x is equal to that expression, and all I have to do is to take the inverse Laplace, and I would have x of t on the left-hand side. That's the solution to my differential equation. And I would have the inverse Laplace of this ratio, this rational function, on the right-hand side. And if I can find the inverse Laplace of this rational function, the problem is done. Now, it's going to be really tough to find the Laplace inverse of this expression, but if I break it down into simpler expressions, I shouldn't have any trouble finding the inverse Laplace of what I've circled here in red. So maybe that's the first thing we ought to do. So we're going to take s cubed plus 10s over s squared plus 1 s squared plus 9, and write that using the theory of partial fractions as, now I see both of these are irreducible quadratic factors, and so I know that this is going to be s squared plus 1. I can't reduce that further, so that's got to be one of my denominators, and the other denominator would be s squared plus 9. And the numerators, if I have an irreducible quadratic factor, is a linear function ax plus b, and the same over here, and of course the coefficients are different, so we'll call that one cx plus d. So using the theory of partial fractions, I should be able to take the expression that we've circled and write it as a linear function over s squared plus 1 plus a linear function over s squared plus 9. Now, why don't we get started on that? And if I multiply both left and right hand sides by the denominator here, s squared plus 1, s squared plus 9, I get a much simpler appearing expression. 10s is equal to, now I'm going to multiply by this product, and you see the s squared plus 1 is going to cancel out. So I'll have an ax plus b and an s squared plus 9, ax plus b, and an s squared plus 9. And the s squared plus 1 cancels with the s squared plus 1. So that's the first term. Plus, now when I multiply here, cx plus d, and I'm multiplying by this product, the s squared plus 9 cancels out, but I'm left with an s squared plus 1. Now I'm thinking how nice it would be. Of course, I did this before I started the video. If I had used A, B, C, and D the same way, but I didn't. So we're going to be doing algebra again here. So let's see what we've got. We've got an A, and this wouldn't be x. This would have been the variable s. No x's. That would have been an s. And so that would have been an s. And that would have been an s. So now let's do some algebra here. I've got an as and an s squared is as cubed. And then plus 9 as plus b s squared plus 9b plus c s cubed plus cs plus d s squared plus d. And this is going to be equal to, now let's get the cubes together. So I've got an a, we're going to get the coefficient of the cubes together, ignore it unless it's a cubed, plus c, no more cubes, s cubed, plus, now we'll get the coefficients of s squared together, b, keep looking for s squared, plus c, oops, no. Oh, algebra requires you to pay attention. bs squared plus ds squared plus, now the coefficients of s, 9a, and just s plus c. Okay, that's it for s. And now constants. There's a 9b, and I see a d right above, plus d. Now what's that equal to? That's equal to s cubed plus 10s. So if the left-hand side and the right-hand side are equal, then the coefficients of like powers have to be equal. So I see that a plus c would have to be equal to 1. The coefficient of x cubed is a plus c on the right and is 1 on the left. And b plus d would have to be equal to the coefficient of s squared. I don't see an s squared term over here, so that would be a 0. 9a plus c, that's the coefficient of s, and so that would have to be equal to 10. And 9b plus d would have to be equal to 0, because there's no constant terms over there. So here's 4 equations and 4 unknowns. I didn't stack them all under the other on a consideration of space. But there's 4 equations and 4 unknowns. Multiple ways to solve these. But if we were going to use matrix theory, we could write this as a matrix equation this way. I'm looking at a plus c. So this would be, the coefficients would be 1, 0, 1, 0. That would be the first equation. B plus D is the second equation. So that would be 0, 1, 0, 1. 9A plus C would be 9, 0, 1, 0. And 9B plus D would be 0, 9, 0, 1. So that's the coefficient matrix. And the matrix of unknowns would be A, B, C, D. And that would be equal to 1, it's this value right here, 0, 10, 0. So there's the matrix equation. Now, using some technology, we would invert this matrix. We would look at this as A plus the, not plus, but times, the unknowns X is equal to B, and then A inverse B would be equal to X. And so we would need some help with the technology. I use my calculator because that's convenient for me. You could also use Maple or Wolfram Alpha, or you could use elimination or substitution or any other way that you know to solve simultaneous equations. When we get these solved, we're going to have that L of X, and this would be picking up right here, L of X. Let's see, I'll get a nice, oh, we haven't used green, nice green color. L of X is this expression, but now we know the values of A, B, C, and D. And so I can write now L of X equals, I'm wondering if I have room here, but I guess I do, 9/8 S plus 0 over S squared plus 1 minus 1/8 S plus 0 over S squared plus 9 is equal to 9/8 S over S squared plus 1 minus 1/8 S over S squared plus 3 squared. And I've written it plus 3 squared because the next thing we're going to do is to go to the inside cover of our textbook and look at the Laplace transforms and figure out what the inverse transform would be. So applying inverse transform to the left-hand side, I get an x of t, and looking at the table of Laplace transforms, and I wish I had one to flash up here, but you can open your book and you can see the table. You'll find that s over s squared plus 1 is the transform of cosine t, and then minus 1/8. And again, look in your book and you'll see that s over s squared plus 3 squared is the transform of cosine 3t. And then just to dress it up, I've got a 1/8 that's common. So I can factor out a 1/8, and I get a 9 cosine t minus cosine 3t. And there's the solution to the differential equation. I hope you liked that, but this is a good introduction to solving equations using Laplace transforms. So I've put up a few more problems in Eraser for you to practice on, and practice is the only way to get proficient. No other possibilities. So watch this video, practice a couple equations, and if I have time, I'm going to try to get together another 5-minute quiz for us next week. So be thinking about that. It will be over Laplace transforms. Elementary stuff, but over Laplace transforms. Thank you.